Hello guys, welcome to today's class. In today's class, we'll be solving some problems on indices. And on the board here, we have about 6 questions we want to solve. We're asked to simplify the following problem. Now, to help you understand the simplification of these problems, you need to have a basic understanding of the laws of indices. And in the last video I explained thoroughly the laws of indices, about 8 laws of indices that will help you understand everything we'll do here. So if you've not watched that video, you don't know the laws of indices, pause this video, go back to the last video I made and understand the basic laws of indices, and then come back as we simplify this problem together. Now, if this is your first time seeing my video, do well to like and subscribe to the channel so you get notifications when I upload new videos. The first problem we want to solve here is 5 to the power of n times 25 to the power of n minus 1, all divided by 125 to the power of n plus 1. Now, in simplifying indices, it is important we try as much as possible to simplify any term to its index form, to its simplest index form. Okay, so the term 25 and 125 should be broken down to its index form. That will help us solve this problem a lot better or a lot easier. So let's take 25. 25, let's break it down to its index form. We know that 25 is 5 times 5, right? 25 times 5 is 25, which is 5 to the power of 2. And this is the index form of 25. Let's also consider 125. Let's break it down to its index form. 125 is 5 times 5 times 5, because 5 times 5 is 25 times 5 is 125. And so this is 5 to the power of 3. Okay, so let's proceed to solve this problem. We have 5 to power n times 25 already is 5 to power 2. Now, but this is raised to power n minus 1. All divided by 125 is 5 to power 3. Okay, and this is raised to power n plus 1. Okay, so this is the first step in solving this problem. Reduce any number to its index form, to its simplest index form. 25 to the base of 5 is 5 to power 2, and 125 to the base of 5 is 5 to power 3. Now the next step is to open up this. This is 5 to power n. Now we need to open up this. Now we know the power law of indices, and that was why I said you need to know the laws of indices so that you can follow through as you solve this problem. Okay, so we know the power law of indices that a to power n raised to power m is equal to a to power n times m. Okay, so when you have a power here, an index number to another power, these powers will multiply. So I will have 5 to power 2 bracket n minus 1. So these two will multiply this power. And the same thing applies to the denominator here, 5 to power 3 bracket n plus 1. Okay, believing you followed through on this, let's continue this solution. Now, this is 5 to power n. We need to open up this bracket here, this multiplication here. This is 5. 2 times n is 2n. 2 times negative 1 is negative 2. Okay, divided by 5. We do the same thing here. 3 times n is 3n. And 3 times 1 is 3. The next thing we need to do is to simplify the numerator. Now, in the laws of indices, we have that a to power m times a to power n, the multiplication law of indices, is equal to a to power n plus n. That when the bases are the same and you're multiplying, you add the powers. So this 5 is the same here, 5, they have the same base. So we are going to add the powers. Take one of the base and add the power. So we have n plus 2n minus 2, all divided by 5 bracket 5 to power 3n plus 3. And this gives us, let's simplify the power here. This is 5. N plus 2n is 3n minus 2 divided by 5 to power 3n plus 3. Now, from this point, we know the law of indices here that if I have an index number, let's say a to power m divided by a to power n, if they have the same base, you subtract the powers. This will be m minus n. So they have the same base here. We need to subtract the powers. And so this will give us 5, 3n minus 2. Then subtract this whole power here, 3n plus 3. And then from here we can simplify. This is 5 to power 3n minus 2. Now, minus into 3n is 3n. Minus into 3 is minus 3. And this gives us 5 to power 3n minus 3n is 0. So we have a negative 2, negative 3. This and this will go out. 3n minus 3n is out. Now, minus 2 minus 3 is 5 to negative 5. And so, from this point, let's take it up here. Let's say we have this. So 5 to power negative 5. We have a law of indices that says if I have a to power negative n, that this is 1 upon a to power n. Okay, so we have a to a negative index is 1 over this number to that index, to the positive form of that index. So let's take it up here. So this will be 1 over 5 to power 5. And this is 1 over 5 to power 5. 5 multiplied 5 times, it's about 3125. 3125. And this will be the solution to this problem. So we've simplified this to be this. 1 over 3125. The next question I want to consider is 3 to power n minus 3 to power n times 3 to power negative 1, all divided by 3 to power 3 times 3 to power n minus 27 times 3 to power n minus 1. And like we did in the first question, we will also break down 27 to its index form. Now, like I said, the best way to tackle indices is to reduce every number to its basic index form. Okay, so 27, we know that 27 is 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. And this is 3 to power 3. Okay, so let's solve this problem. We have 3 to power n minus 3 to power n times 3 to power negative 1 all over 3 to power 3 times 3 to power n minus 27 is 3 to power 3, right? So we have 3 to power 3 times 3 to power n minus 1. Okay, so let's take the next step here. Now the next step will be to break down this 3 to power n minus 1, to split it out, right? To split it out. Okay, so let's go. We have 3 to power n minus 3 to power n times 3 to power negative 1 divided by 3 to power 3 times 3 to power n minus 3 to power 3 times 3 to power n. Now, we can break this apart. We know that 3 to power n minus 1 is something as 3 to power n times 3 to power negative 1. According to the law of indices, law of multiplication, that when the bases are the same, you add the power. So this is, we can split this to this. So we have 3 to power n times 3 to power negative 1. We've splitted this to be this. Now from here, we can now factor out some common terms, right? We can now factor out some common terms. Here we have 3 to power n. We also have 3 to power n. So we can factor out 3 to power n. If you factor out 3 to power n here, right, we'll be left with, if I factor out 3 to power n from this, I will have 1. Now, the idea of factorization, to factor out, is more like to divide out. Okay, let me make it a bit easier to understand. So, let's say the common term here is 3 to power n. What we always do is to say 3 to power n, this divided by this, divided by 3 to power n. This value divided by this is 1. You write the 1 inside in negative. Now this whole term divided by this, if I have 3 to power n times 3 to power negative 1 divided by 3 to power n, this will be left 3 to negative 1, and that is what will remain here, 3 to negative 1. Okay, so the idea of factorization is more like this factor should be able to divide each of these terms without a remainder. Okay, so we can now have divided by what is the common term here. We can factor out 3 to power 3 because it's here and it's also here. We can also factor out 3 to power n because 3 to power n is here, it's also here. So let's factor out 3 to power n, 3 to power 3, 3 to power n from this denominator. From here, we have 1 minus from here, we have 3 to power negative 1. Okay, so we can see that this can strike out this, and this can strike out this, and we'll be left with 1 over 3 to power 3, 1 over this. And this is 1 over 3 to power 3 is 3 times 3 times 3. 3 times 3 is 9 times 3 is 27. So the answer is 1 over 27. The next problem we want to solve is the square root of 160r squared plus square root 71r to power 4 plus square root 100r to power 8. Okay, to solve this, okay, let's take this part as our rough part. Let's take this part as our rough part. So we are going to simplify this problem by solving each term in this given problem. So we are going to start with the inner term here, simplify it, and keep on resolving till we conclude the solution to the problem. Okay, so first we will want to tackle this. So let's say this is equal to 160r squared plus root 71r to power 4 plus, now let's simplify this in this rough part. Let's simplify this root 100r to power 8. So we have root 100r to power 8. Okay, how do we simplify this? Okay, let's take this as 100r to power 8 or to power half. We know that the square root function is more like to power half. This square root value is that given number to power half. Square root of any number is that number to power half. Okay, so we've written this as this. Now, like I said in the previous example I solved, the best way to tackle indices is to simplify the terms, the numbers in that problem. Like this 100 will reduce it to its index form. Okay, so we know that 100 is 10 times 10, which is 10 to the power of 2. So we can write this as 10 to power 2, then r to power 8. Now this is to power half. Now, according to the product power law, which says that a b to power m is equal to a to power m, b to power m, each of these terms will be raised to this power. So we have 10 to power 2 to power half, this to power half, r power 8 to power half. And if we want to simplify this, this is 10. Now the powers will multiply, right? So this is 2 times half, r 8 times half. 2 times half is 1. Okay, because 2 times 1 is 2, divided by 2 is 1. So this is 10 to power 1, which is 10. And this is 8 times half. 8 divided by 2 is 4. Okay, so this is r to power 4. So we can rewrite it here as 10r to power 4. Okay, so we've simplified this expression to be this. Now let's continue this solution. 160r squared plus, now let's simplify this. So because this 2 is in terms of r to power 4, 71r to power 4 plus 10r to power 4. So they can add because they are like terms, right? They can add now. So 71 plus 10 is about 81r to r to power 4. Okay, so the next part is to go on again We have 160r root to power 2 plus. Let's now simplify the root of 81r to power 4. So simplifying square root of 81r to power 4, we have this as 81r to power 4 to power half. Like I said, the square root is to power half. Okay, so simplifying 81 in this index form, we have that 81 is 9 times 9. So 9 to power 2 is 81. So we have 9 to power 2 root to power 4 all to power half. Now, there are several ways we can actually simplify this. Some persons could say, just say this is root 81 times root r to power 4 from this point. But I don't want to go through this process. I want to see or simplify this whole problem by breaking these numbers down to their index form instead of just solving directly. Okay, so let's we'll take this off. So let's come back here from this point. So we have this is 9 squared all to power half, like we did in the previous explanation here. When we got this term. Okay, I think it's about this term. Okay, so let's take it bit by bit. This is 9 to power 2 all to power half, r to power 4 to power half. Okay, so we know what to do here. The powers multiply. This is the power law of indices. So the power multiplies and you have 9 2 times half times r to power 4 times 1 over 2. Okay, so this is 2 times half is 1. 2 divided by 2 is 1 times 1. So we have 9 r, 4 divided by 2 is 2. So this is 9r squared. So we write 9r squared. So we simplify the root of 81r to power 4 to be 9r squared. Now the next step is to add up because they are now like terms. This is r to power 2, r to power 2, like terms. So this gives us 160r squared plus 9r squared. 160r squared plus 9r squared is 169r squared. Okay, so we can actually just say this is the root of 169 times the root of r squared and so on. But I also want to break this down to its index form. So this is okay, let's still do the rough part here. Let's simplify here and write the final answer here. So simplifying the root of 169 r squared, we'll have 169 r squared to power half. Okay, so this gives us 169 is 13 times 13, which is 13 squared. Okay, so we'll have 13 squared, 13 squared r squared, all to power half. Even at this point, you can take another law of indices, which is the product power law. Say something like 13r to power 2 all to power half. You can still approach this. So in indices, there are several ways you can resolve a problem as long as you know the laws of indices. You can use the different law to simplify a problem. Another person uses a different law and still gets the same answer. So, but you need to understand the laws of indices. You can now use any of the laws to your advantage and solve the problem. But I want to go with my usual method, which is 13 squared to power half, r squared to power half. Okay, so this gives me 13. This is 2 times half. 2 times half, which is 1. Because 2 divided by 2 is 1 times this. So this is 2 times half is still 1. So this is 13r. And this gives me 13r here. And that is my answer to this problem. The next question on the board here is the third root or the cube root of 64r to power negative 6 or to power half. Let's simplify this problem. Okay, so to solve this, we can take this through different methods. You can simplify this problem through different methods, through different approaches. Okay, so anyone you do, as long as you are following the laws of indices, you can still arrive at the same answer. Okay, so let's just work with a method I have in mind. So let's say this is, okay, let's simplify this as 64r to power minus 6 raised to power half or raised to power 1 over 3, because we know that this cube root function here is power 1 over 3. This cube root value here is all of this to power 1 over 3. So that is just the simplification I'm doing here. Okay, so we can actually start solving this problem from inside. I mean, simplify this 64 to its index form, or we can gradually break in from outside. Any method, any approach is fine, as long as you are using the right laws of indices. Okay, so let's see what we'll do here. I can say, okay, let me gradually approach this from outside, right? Let me approach this from outside, yeah. So I have 64 r to negative 6. Okay, so I have this. Now we know the laws of indices. The power law of indices, like I said earlier, a to power m or to power n is a to power m times n. So this is a value to a given power or to another power. So these two powers can multiply. So let me multiply the two powers. So this is 1 over 2 times 1 over 3. And this gives us 64r minus 6 to power. This multiplies, we have 1 over 6. We have 1 over 6. Now, I can't just take the power law here, just this and this. I can't just take, because this is multiplied to something else. So I can't just apply power law on this, because there's a number here for multiplying this value. So they are together. So anything I'm doing should also affect this 64. So first I need to break this 64 to its index form. And what is 64? Okay, 64 is 8 squared. Okay, we can also see 64 as 2 to the power of 6. Right? So this is 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2, 32, times 2, 64. So this is 2 to the power of 6. Now, if you also want to, another way to understand the index form of this is, say, 64 is 8 to power 2, right? That's 8 times 8. So if you have 64 as 8 to power 2, you already know that this 8 is 2 times 2 times 2. Okay, so this is to power. So this is 2 to power 3 or to power 2. So this is 2. This 2 multiplies. You have 2 to power 6. So anyhow you want to reduce it to its index form is fine. But the truth is 64 is 2 to the power of 6. 2 to the power of 6. So we can write this here as 2 to the power of 6 r to the power of negative 6 or to the power of 1 over 6. Now, at this point, you can still use different method. You can use the division law of indices here. You can apply division law of indices here. You can say 2 to power 6 r to power negative 6 is the same as 2 to power 6 over r to power 6. This is correct from the division law of indices. That when you have okay, so this is not really the division law of indices, but we know that from the negative index law, yeah. So this is from the negative index law, where you have root to power negative 6 to be 1 over r root to power 6, right? So this is the application here, more like 2 to power 6 times r root to power negative 6 is 2 to power 6 times 1 over r root to power 6. This is 2 to power 6 over r root to power 6. Okay, so we apply the negative index law here to break this down. Okay, and if we also use the quotient power law, yeah, quotient power law, this can be written as 2 over 6 to power 6. Remember the quotient power law we discussed? I think that was the seventh law we discussed in our previous video, that when you have a division of numbers to a given index, that each of the numbers can be taken to that index. Okay, so this is this. We can approach it this way. Okay, but I will still want to use the usual method I've been using, where I will say that this is 2 to power 6 or to power 1 over 6. Okay, all to power 1 over 6, the product power law, that each of, when there's a product, each of this term can be raised to that power. So this is times r root to power negative 6 raised to power 1 over 6. Okay, let me continue with this. This is the power law of indices, that when you have an index number, okay, raised to another power, that the two powers multiply. So this is 2 to the power 6 times 1 over 6. R root to power negative 6 times 1 over 6. This gives us 2, because this is 6 divided by 6 is 1. 6 times 1 times 1. Okay, so this is just 2, right? Now this is R. 6 times 1 is 6 divided by 6 is 1. So we have a negative here, negative 1. And this simplifies to 2 times 1 over r. Remember the negative index law, that when you have r raised to power negative 1, is 1 upon r. So this gives you 2 over r. And this is your answer to this problem. So when you have this problem, this is the answer to the problem. All right, we are the fifth problem now, and this is a very interesting problem. Okay, so let's pause a bit and test our brain with our understanding of perfect squares, and then see how we can use it to solve this problem. Okay, so for perfect squares, let's start with 1 squared. 1 squared is 1, 2 squared is 4, right? 3 squared is 9, 4 squared is what? 16. 5 squared is 25, definitely. 6 squared is 36. Let's continue and let's see how far we can go. So 7 squared is 49. Okay. 8 squared is 64. 9 squared is 81. 10 squared is 100. Okay, let's continue. Let's see how far we can go. 11 squared is 121. 12 squared is 144. All right. 13 squared is what? 169. 14 squared is this is 196, right? Yeah, I guess I'm correct. Okay, let's go to 15 squared is 225, right? 16 squared is 16 squared will be 256, right? 256. Yeah, that's correct. 256. 17 squared. Okay. 17 squared will be 289. 18 squared is 324. I think that's correct. I hope so. 19 squared is 19 squared. This should be 361. And 20 squared is 400. Okay, let's stop it here. And I hope we are all correct in this perfect squares. And then let's see how we can use this knowledge here to solve our problem over there. To solve this problem, we are going to reduce each of these terms to their index form, like we always do. But this is a bit simple. We know that 85 to the power 0, anything to the power of 0 is 1. So there's no point simplifying this to any index form. So we just evaluate that one to be 1. Okay. Now this is 225 to the power half, more like the square root of 225, but I will not want to go with the idea of square roots. I want to simplify to the index form. So let's simplify to the index form. Now 225 from here, let's borrow the idea from here. 225 is 15 squared. Okay, so that's 15 times 15. So 15 squared is our 225 to the power of half. So definitely you can see here that the square root of 225 will be 15, because 15 squared is 225. But let's just take it gradually from this angle, from this point here. So plus, let's just evaluate this one as 1. 85 to the power 0 is 1. Now times, now 256 from here, 256 is 16 squared. Okay, so 16 squared. And it means we can actually keep this in the base of 2. In the base of 2. So if you have 16 squared, so let's just approach it as 16 squared first and gradually reduce. Okay, so we have 16 squared. So this is 256, 16 squared to power negative 1 over 4. All right, let's continue solving this problem. Okay, so from the power law of indices, we have that this will multiply this, right? Because this is to a given index, now all to another index. So the powers multiply. So 2 times 1 over 2, 2 times half is definitely 1. So this is just 15 to the power 1, which is 15. So we have 15 here, now plus 1 times, uh, this itself is 16. 16 is 2 to power 4. So we can evaluate this as this is 2 to power 4, all to power 2, all to power negative 1 over 4. Very interesting. So uh, we can actually multiply all of this together. That's correct. Or we can do then bit by bit. That's still fine. So we can actually say 4 times 2 is 8, then multiply. Anyhow you want to approach it is fine. Anyhow you want to approach it is fine. Okay. Okay. So, but let's just take it bit by bit. There's no need to hurry. Let's just take it bit by bit. This is 16. So let's just take 16. Now 2 times negative 1 over 4. So let's the power just multiply. This is 2 times negative 1 over 4. And this gives us here, we have 16 here because 15 plus 1 is 16 times 16 to power 2 times negative 1 over 4. 2 times negative 1 is negative 2 divided by 4 is negative 1 upon 2. So we have a negative 1 upon 2. This is an interesting one. Yeah, so there are several things we can do here, definitely. We can see that there are several things we can do. There are several things we can do here. Yeah. Okay. So what do we do? Because I'm seeing lots of laws of indices I can apply here. But we know in the idea of mathematics is to make things simple, solve a problem, and use a simple method. So I'm actually thinking I can say 16 to power 1 times 16 to negative power, add the powers. I'm actually thinking about that. But I'm also thinking I can actually reduce this. Anyhow I want to solve it, I'll still get the same, I'll still get the answer correct. So let me just say 16. Let me leave that idea of 16 to power 1 and just work this out. Okay. Okay. Or I can actually reduce 16. I can actually reduce 16. This is 2 to power 4, right? Let me just, we'll be working with reducing these numbers to their index form. So let me reduce 16 to its index form. That's more interesting, right? So this is times 2 to power 4 all to negative half. Okay. So this gives me 2 to power 4 times, this is 2 to power 4 times negative half. This is 2 to power 4 times 4 times negative half. 4 times negative 1 is negative 4. Divided by 2 is negative 2. So this is 2 to power negative 2. All right. At this point, I can now apply my product law of indices or multiplication law of indices, where they have the same base, the powers add. But in this case, because this is a negative, I will subtract. So this is 2 to power 2, and this is 4. And that is the solution to our problem. Let's go to the next problem. Before we go to the next problem, please look back at this and ensure you've mastered this values here, the perfect squares from 1 to 20. It will do you good if you master the perfect squares from 1 to 20. This is the last exercise for today, and I believe at this point this is pretty much simple for you. You should be able to tackle this without any stress. From the ones we've solved before, from number 1 to number 5, this is very simple to tackle, right? So I will give you some time to solve this problem and get your answer, and then come back. Let's see my own solution to this problem. Believing you've tried this problem, let's solve this together again. So here, like we always say, like I would always say, I prefer to reduce these numbers to their index form, to their basic index form. Now this is in index form, but we also have basic index form. So to the base that cannot be splitted down to any other simpler base. Basically, more like prime numbers, prime bases. Okay, so let's tackle this. So 4 is 2. Now we can actually keep this to the base of 4 too, you know. But like I always say, let's go back to the basic index value. Okay, so this is 2 to power 2 or to power negative 1 over 2. Now 16 is 2 to power 4 or to power 3 over 2. Sorry, 3 over 4 divided by 2 to power 2 or to power 1 over 2. Okay, let's continue here. Now, this multiplies this, the power law of indices. So this is 2 raised to power 2 times negative 1 upon 2 times 2 raised to power 4 times 3 over 4 divided by 2 to power 2 times 1 over 2. Okay, so this gives us 2 to power 2 times negative half is negative 1, right? Because 2 times negative 1 is negative 2 divided by 2, negative 1. So this is negative 1 times this is 2 to power 4 times 3. No, 4 divided by 4 is 1 times 3. So this is 3 divided by, so this is 2 to power 2 times half is 1. Okay, so that's just 2. So here we have, let's apply the product or the multiplication law of indices here. So the base are the same, we add the power. So this is definitely negative 1 plus 3 divided by 2. And this is 2 to power 3 minus 1 is 2 divided by 2. You know, there's a power here 1, 1, 1. So let's just complete the laws here. So this is division, the division law of indices. We say when you are dividing and they have the same base, you subtract the powers. So this is 2 to power 2 minus 1. And this is 2 to power 1, which is definitely 2. And this is our solution. So far we've considered about 6 problems, 6 solved problems on indices. And I believe with these practical examples, you should be able to tackle different problems on indices. Now look out for part 2 of solving problems involving indices.